Welcome back. This is an example to introduce the setup of networks around prediction, and we call that contracting as an example to get the proper language game about what neural networks are about. So we discussed that in previous chapters. So and I want to just go for a more extended example. With classification it was more simple last chapter. Now we want to go and ask for a weather forecast to go in an application you might of some use, so you get an idea of how these things work. With a very surprising distinction with that a weather station can predict the temperature of the next day with temperatures of previous days with a certain accuracy. But if you connect weather stations in the grid over an area, and if you put them into a neural network, they all learn from each other and get better predictions. So this will be part 2. So that's very interesting to see how these things work out. Again, our very principal setup, how to go for how to set up networks. So in this case, this is there's a repository of Wolfram to get weather data from any point, a weather station, a lot of them in the world. So now we can make a plot for the year 2019 in Zurich with the mean day temperature, and this is how Zurich looked like. So what we want to do is we take the weather data from 2010 to 2020 in a day. And then we take always, we split that into 5 days, chunks of 5 days, and we take always the first 4 days to predict the 5th day. So that's very simple. So we make a partition in 5 with an overlap of one. And then each chunk we simply say take the first one on the input and predict the next one. And then have it for a year, have it 365 times. So these are then our data. So we can check it, data 2. The first one is this. And now if we go to the second one, it's moving. The second one, it's moving once, so you see it's this value is and then it predicts this one. So it's moving across all the days like this. This is what our data is looks like. It's here. Good. So that's our how to get data data samples. It's we can check what are the lengths of it. So we have about 4,000 days of 10 years. So then we say our training data is the first 9 years, and then the last year, the 10 years, or the 2020 then, is the validation test. So just to get an idea of how accurate this training works. So you see it's the same setup. Getting data, looking for the data samples, setting up the network. So it's very schematic as well. So what we have here, 4 input and a single output as a scalar, it's not a list. So therefore we say linear here 4, we add another linear, we have a linear for 1, flatten that to make the vector here a scalar, and then having the input 4-dimensional, output a single number. So this works here, and we can look for the weights, and then you see it's 16, 20 weights here, 20 weights here, 4 weights here, so it's 44 things to train, parameters to train. So it's not a lot, we can increase it. So now the training itself is always the same, exactly the same code, just look how it works. So it's going good pretty soon. There is a clear distinction between the validation set and the training set, and it's not going down too far, so it's just in percentage. So it's 4 or 5% is it's a difference of 4 or 5%. So and this means stop it. It doesn't make sense to continue. So we can ask for measurements as we did before. So it's a loss of 5%. So then next step, running, and that's it. Yeah. So therefore we can simply ask, what is day number 202 of the data n of the validation set of 2020? So, and then this is the day. We take just these temperatures of the 4 preceding days and ask our network, it's here, with this, and round it to 0.2 just to get not too confused with the numbers. So this means the prediction is 30.6 instead of 14.6. So you see, not like we had seen before, it's real life data 19 to 21. So it's not too good, but not bad as well. Yeah. So we can go for beginning of the year, and it's not too bad in predicting from out a sequence of temperatures the system didn't know before. So not too bad in this difference. If you want to see the plot, so this is a little, so this is quite convincing. So you see the real things and then the predicted things of 2020. So of the validation set, you see it here. So you have one plot is the data, the actual data, all just this, and this is the prediction on the first one. So you take this and make the second line. But this is a little misleading because these are the errors. So now I just subtract these two things and put them on a line, and then you see the errors in degrees. So they are pretty bad predictions. Good. If you go with the trained, you see this, for example, it's misleading. It doesn't help. It just looks like this. You simply say, "Wow, this is super good." So you have to look at it like this again with the trained data. So this is the data he knows, and then prediction is like this. You can improve this with the known data just by adding more parameters, but this doesn't help. So if you put here more parameters, so you can match to the known things to absolute precision. If you give a lot of parameters, then everything can be adapted. But we want to predict things you don't know, and then this doesn't help. Good. That's the first scenario. A slight change, and we go for we go for another setup. So we have here, we simply go here for this takes a little time, therefore I'm just discussing it. We have weather data, and we make a grid of weather stations. So we can find weather station by geoposition, and then we go and make a grid of 5 by 5 weather stations around Zurich. This is Zurich. And around Zurich, we look for the nearest weather station and get their data. So then there are 25 weather stations, and then we have to correct them a little because a few days some of these weather stations didn't work in a few days, and then we simply have to take these days out. So this is done with data here. This takes a little time, so therefore you can look the code if you like. This is the shortcut to it. So we put it to the cloud to get the data. So day one is this, which simply means we have 25 by 4 days. So this is the first weather station, the first 1, 2, 3, 4. So this is the first weather station. Preceding days, second weather station, and so on, 25. And this is the prediction, this is the next day or the current day temperature with these preceding days. So this is 25. So it's 25 and this is 100. So with computing and with neural networks, you should not be afraid of huge dimensional spaces. So now we have 100 towards 25. So this means, so let's for example make a prediction just for a single, make a data set just for a single weather station. So which means we need this cases command on this data. We take A as a key, we take A rule B. So then it matches with A would be this left, the inputs, and B would be this, and for all these things mapping in data on level 1, so this will be 3,900 times, we say A should rule by B of weather station 13, so it's one of this, just take this. If we do this here, then data 4 of 1 is just the 100 dimensions in, and then the prediction, then the actual temperature of a single weather station as we had with our first example. But now we have 100 dimensions input and not only 4. So this weather station here takes into account all its neighbors for prediction, and we'll see what happens. So it's so again, now this the training data, validation data, I put a 2 in to make this different. So the same like we had before. The setup of the data, it's the same as we had, but now we take, instead of 4, we had here 50 dimensions, 20 dimensions, we go down to 1 dimension, flatten it to get this color, from 100 down to this, which means if we ask for no, it's not there, so we have to go here. Let's go here for, no, it's enough. So therefore, for example, here the second layer, linear layer, now it has 20 by 50, so it's 1020 parameters. This one here has 5050 parameters. This one here has 20 parameters. So it's 5,000 to 6,000 parameters to learn. So that's much more resolution in doing it. So so now you see it doesn't matter. The training is just the same code. It just goes there. And you see already the precision is better than we had, around 5%. Now we are around 4%. But it's not improving anymore. So you see this network is very, very good. So this training set gets adapted better, but the validation that it doesn't get better. It's always around this. So we can stop it and ask for for the quality, and then we see the losses is 4%. So therefore we have better prediction just because of getting friends with the other systems. Now, of course, now we can make the whole grid, and this is done with just the data. So we had data 4 was this one, and now it's super simple. Now we simply say with our network we just take data, not data 4. With a specific weather station, we take all the weather stations, just have an output of 25 dimensions and take data. So our data T is data with 100 dimensions toward 25 dimensions, the same with a validation set, but this. Our network is again very, very similar. So we have 100 to 80, 100 in to 80, so it's 8,000 to 40, it's and then to 25, no scalar, it's a vector of 25 to have no, this is to have this thing as a network, and we train that, measure that. And it's the same line of process to do these things. So it's not improving. I think you can do a little by getting more parameters here, but it's just, so it's 6.6. You can't compare it with the other setup, with the one dimensional in the error. But now if you ask for a prediction of day number 120, you get all the weather stations. So the real value here and the predicted value as a column, real predicted, and it's not bad how it works, yeah? So this is about prediction. So the key interest, the important thing to realize is these are the two principal schemes. You see where the complication is. It's about getting and curating the data. The scheme here is always the same. The setup of a network is not too complicated. You simply have to understand what a linear layer is and how to deal with these vectors and get them up and down, and how to add more parameters. So to get more resolution, but that's it. It's super generic how to make that. And this is what I want to show and what you get an impression with. So there are two very principal views to it, but with the classification and the prediction, or the differentiation and the contracting, I would say. But at the end you see it's not too different in how it is done. Internally it's just the same mechanism. So this mechanism is working for everything you can imagine, because it's alien. Thanks for watching. We will have two small chapters today left. This is on discontinuity, and the other is on locality. These needs to be introduced. We had the ramp already with the discontinuity for the classification. We will go in depth and see what it is good for, because you need a certain view towards the alienated code is about, and how to get the differences. And these are two concepts we still have to discuss. That's it in this chapter. Thank you for watching, and see you soon.